So for the roots of a polynomial function, remember that they could also be called zeros. And remember that the total roots equal the degree. We learned that last class. That's the fundamental theorem of algebra. And then also remember that real roots are x-intercepts. So total roots are going to equal the degree. All right. Very good. 2 turning points, 1, 2. Josiah and Owen, what do you want to share with us? Alexa.
Domain is negative infinity and positive infinity.
Yes. So this one keeps going to the left and this one keeps going to the right. So that is our domain, negative infinity to positive infinity.
Total zeros / roots are 3. Real roots are 1. And non-real roots are 2.
Okay, let's go through that. So total roots equal the degree. Real roots, you can see it on the x-axis, just one of them. So that means if there are 3 total and only 1 is real, then there are 2 that are not real. Very good. Right here. Good. So the y-intercept is the point 0, 1. So it's increasing from -1 to +1. Good. Good. Leading coefficient is in front of the leading term. Remember that if it's not in standard form, you have to find your leading term because that would be the one with the biggest degree. But this is in standard form. So we're going to use that -0.25. Okay, let me try to catch up to you. Very good. Okay, so as x goes to negative infinity, the y goes to positive infinity. As x goes to positive infinity, the y goes to negative infinity. Well done. Who wants to share something else? Good. So the range is going all the way down and all the way up. So negative infinity to positive infinity. And we have some decreasing intervals. Is that what you're going to give me, Blaine?
Would it be -1?
Let's see. Negative infinity to -1. Good. Do you know the other one? 1 to positive infinity. Very good. All right, and then state the zeros from the graph. That just means tell me the actual number of the zero. So you should have put 2. So making connections between the equation and the graph features. So I have an equation here, and I also have it factored. Just want to review factoring for just a second. There's a bunch of different types of factoring. This one you are actually capable of factoring so far, because we can see there's a common factor of x. And if I divide each term by x, I get x squared plus 1x minus 2. And then I'm looking for the numbers that multiply to -2 and add to 1. And those are 2 and -1. So this becomes this then. Okay? So this is my factored form. This is my standard form. Looking at this equation, what is the degree? The degree is 3. The total number of roots and the root from the graph. So the total number of roots is the same. We're going to graph in Desmos now. So if you don't have your computer out, let's get the computers out. Notice that when you graph it, not only does it give you precisely your x and y intercepts, which you want to make sure you graph precisely, It also gives you your turning points, which are usually not as nice numbers as the others were. Okay, but we're still going to do our best to graph them as accurately as possible. So I'm going to start by graphing my zeros at -2, 0, and +1. And then I'm going to try to graph my turning points. I'm not that precise at graphing, so I'm just going to think of that as +0.5, -0.6. Oops. And then this one, -1.2, 2.1. All right, and then you're going to try to sketch that on your graph. That's an excellent question. Can anybody answer that? What's the y-intercept? 0, good. So our x-intercept is 0 and our y-intercept is 0 in this case, right? Okay. All right, so I just drew that little sketch based on what we had there. So the roots from the graph, we said, I'm going to make a set here. -2, 0, and +1. And then, like Blaine reminded us, the y-intercept is 0. All right. So as x goes to +infinity, what is the y going to? +infinity, good. Normally I write f of x, but I'm just running out of space, so I'm going to put y goes to infinity. And as x goes to -infinity, what is y going to? -infinity. Okay. Leading coefficient. I don't see a number there, so what would it be? It's 1 if you don't see a number. So your leading coefficient is 1. So now it says, make a connection between the factors and the real roots. So here are the real roots, and here are the factors. I want you to write something on your paper, and we'll share in just a minute. Okay, raise your hand if you're ready to share something. I see one hand, 2 hands, 2.5. Blaine, what did you have? So both the roots and the factors have -2. So in the factors, oops, up here I see a +2, and then the root I see a -2. Is that the connection you're making?
Oh, I thought you were talking about the first one.
Oh, here, yeah. Okay, so I do notice that there. But at this time right now, we're just making a connection between the factors. But we'll keep that in mind, okay? We'll come back to that. All right, I see a third hand. Josiah, what did you have? Oh, you saw a connection. So you saw a -2 here and a +2 here?
Yeah, and then the negative one.
Okay. And then what about that one?
That's getting 0.
This is the 0 here. Okay. Sally, did you have something similar?
Yeah, I said that the real roots are the same as the factors, but the signs are flipped.
But the signs are flipped. And that's something similar to what I saw that Asan had, right? Did anybody else have something like that?
I thought it was like the inverse.
So, okay. So actually, I think you're onto something with that term inverse. We use inverse operations in order to solve equations, right? So if I were going to solve this factored equation and set it equal to 0, so if I solved x times x plus 2 times x minus 1 equals 0, the zero product property would tell us that one of these has to equal 0. And then just like Steph was saying, we could use inverse operations to solve them, right? So we would get x equals 1, and we would get x minus 2 equals 0. So we would get x equals 2. And of course, this is just x equals 0. So these are all very good. yes, the zeros were opposite of the roots, and yes, we use inverse operations to solve these equations. So the roots are the zeros of the factors. Now, if you already wrote something, that's good too. But putting together everything you guys shared, roots are the zeros of the factors, would be helpful. And actually real roots. Well, actually, even non-real roots, if we had a factor that had non-real roots, you could also set that equal to 0. All right, well done. Let's see if you can start this one on your own, okay? You're going to find the degree, total number of roots, and then to find roots from the graph, we're going to graph it in Desmos. All right, so get started on that, please. All right, so once you have it graphed, make sure that you graph your zeros, your y-intercept, and your turning points. So you want all of those on your graph. So I'm going to graph my zeros at -1, +1, and +3. And my y-intercept at +3. And my turning point is about -0.44 and 2.44. It's kind of a pretty graph. Looks like an M. All right, what was the degree?
4.
It's 4. Now you could find that because there are 3 turning points, or you could find that because the biggest exponent is 4. We have a lot of info here, which means the total roots are 4. On the graph, how many different roots did we find? 3. That's problematic. So we got -1, +1, and 3. Did you guys find the y-intercepts? 3, okay. And behavior. So I'm going to start it out as x goes to +infinity, as x goes to -infinity. All right, so what's happening on the right side as x goes to +infinity, y is going to what? -infinity, because that side goes down. And as x goes to -infinity, y goes to -infinity. All right, what was our leading coefficient? -1. So I see a negative sign here, and if you don't have that number 1, you can put it in, because 1 times anything is itself. All right, so here's the big question. So this problem has no non-real roots. If you were tempted to say it has 1 non-real root, remember that non-real roots always come in pairs. And if you think about the quadratic formula, remember when we used the quadratic formula to find complex roots that had an I in them? It was a plus and a minus. So the plus gave you 1, the minus gave you the other. All right, so you always get complex roots in pairs, either 0 or 2 or 4 or 6, but never 1. So I want you to look at the graph, look at the equation, and talk to your group about how can it be that my degree is 4, but I only have 3 roots listed here. Okay, so what you guys shared with me was the factor x minus 1 happens twice. So x equals 1 is a root twice. So really our roots are -1, +1, +1, and 3, but we don't make a list and write things twice like that. Okay? So we still just write it once when we're writing our roots, but in our heads we know it's counting twice. And that's how the number of roots can still equal the degree. Okay, here we go. Multiplicity. So when your factor happens just one time, like this one here, f of x equals x minus 2, you can set that factor equal to 0. And you find that it's going to pass through x equals 2 right here. But it's just going to pass straight through like that. All right, so when your multiplicity of the factor is 1, multiplicity 1, it passes through the x-axis. Okay, multiplicity 2 is what we just noticed. We still get x equals 2, so there's still a 0 at 2. But when the multiplicity equals 2, multiplicity equals 2, then it bounces off the x-axis. So like that. Oops, you guys can't see. All right. So that kind of looks like a parabola, right? Which is a quadratic equation. The cubic equation we learned last time has different forms, but one of them is kind of like a quadratic where the left side goes down, and that's the same thing that can happen here. So when we still have x equals 2. When we have to the third power, multiplicity is 3. Some people call this a sidestep, and some people call this a wiggle. And that's up to you. You can choose if you want to call it a sidestep or a wiggle. So it passes through, but notice it doesn't pass straight through like 1. So it's a sidestep or a wiggle. Okay. And then if you have something like this, notice it says x squared plus 2. If I set that equal to 0, I get x squared equals negative 2. And x is going to equal plus or minus the root of negative 2, which is I root 2. So I root 2 is nowhere on the x-axis. It's not going to have any x-intercepts. Okay, so it does not touch the x-axis if the roots are complex or imaginary. So this is an actual polynomial equation, and here is the factored form of it. So each factor gives us a 0. What 0 do we get from x plus 7? I heard a negative 7. Does that make sense? If I set x plus 7 equal to 0, I'll get negative 7. What's the multiplicity of that factor? How many times does it happen? Just one time, because you don't see an exponent, so that means it happens just one. And we're going to say that passes through. The next factor is a little tricky because it has a 2x plus 1. So if I set 2x plus 1 equal to 0, what do I get for x? Let's try it. I don't really have any room, but I'm going to try it over here. 2x. Yeah. Will you say that one more time?
What makes it negative plus?
Negative 7. Let me solve this one and then I'll go back to that one, but I think it'll become more clear after this one. So each factor gets set equal to 0. And in this case, I'm going to subtract 1. So I'll get 2x equals negative 1. And then I'll divide by 2. And I'll get x equals negative 1/2. Does that make sense then for the other one? If I set x plus 7 equal to 0,
Yeah.
I'll subtract the 7.
Can you put a decimal or is it actually a fraction?
If you have an exact decimal, that's fine too. All right, what's the multiplicity of this factor? 1, so it also passes through. And what's the multiplicity of the last factor? 3. And what's the 0? 4. So if I set x minus 4 equal to 0, I get x equals 4. If the multiplicity is 3, then what happens? Wiggle or sidestep. I'm going to write them both because some people like one, some like the other. You can only write one if you want. Okay. The total degree, we can see in the original equation, the total degree is 5. But if you only had the factored equation, you could still find the total degree because you would add up the exponents here. So I have 3 plus 1 plus 1. That also tells me that the degree is 5. Or if you have the original, you can just look for your greatest exponent. The next one is not factored for you, so we have to factor it. What would be the first step in factoring that? So I think it is in standard form. What kind of factor should we look for first? So yeah, you guys are thinking ahead on me. You guys are really thinking about factoring, but you're just a little bit ahead of me. Before I can look for numbers that multiply to negative 8 and add to negative 2, I have to take out the what? The common factor. What common factor could I divide all these terms by? And more than just x to the 1, I could get rid of x to the 2. So I can take x to the 2 out. And when you divide each of these by x to the 2, remember that when you divide, you subtract exponents. So I have x to the 4 over x to the 2. That gives me x squared. Minus, the 2 will come down, and I subtract these exponents. I get x to the 1. And these x squareds cancel out altogether, like that. So first step was to take out the common factor, and then what you guys were getting to before, I have to find the numbers that multiply to negative 8 and add to negative 2. What are those numbers? Multiply to negative 8 and add to negative 2. So negative 4 and positive 2, they multiply to negative 8, they add to negative 2. So now I've got my factored form. All right, if I set x squared equal to 0, what do I get? X equals 0. Multiplicity? What's the multiplicity? 2. And what happens when you have multiplicity 2? It bounces.
Wait, I know it's 2 for 0.
It's this squared right here. You see that? That's where we get the multiplicity. All right, x minus 4, what's the 0? Positive 4, and the multiplicity is 1, good. And then it passes through. And x plus 2, the 0 is multiplicity, and also pass through. And what was the total degree? 4. All right, so some of you are going to be catching up right now. Some of you are reading ahead about these conclusions. So I've been pausing it in between, but I am recording. Thank you. Yeah, it's a little late. All right. So here are the things we're making conclusions about. First, about end behavior. When the leading coefficient is positive, the right side goes to blank. When the leading coefficient is negative, the right side goes to blank. And why do you think that's true? So I want you to consider not only 3 and 4, they both have leading coefficients that are positive, but also, and actually even more important, leading coefficients from 1 and 2, because we have the graphs right here. Okay? All right, so what we noticed was when the leading coefficient is positive, the right side went up. When the leading coefficient is negative, the right side went down. Positive is up or to positive infinity. Negative is down or to negative infinity. So, okay. All right, let's put this down. I'm going to say that they match, the two ends match. So both up or both down. And this one they don't match. So you have one up and one down. Okay. I don't. Okay, so the degree being even and odd, we just looked at these two right here. Here is an odd degree, right? And so this one, the ends did not match. And then this was an even degree, and the ends did match. We also have this one here. This one had an odd degree, and the ends did not match. You see how one's up and one's down? Yeah. All right, so I didn't have a really good explanation. I wondered if anybody else had a better explanation. All right, well, let's just think about the turning points, right? If the degree is even, we can have an odd number of turning points. So if I turn an odd number of times, I end up going the same way. Like one turn, right? They're going to be up and up. If you have 3 terms, you go the other direction, and then the other direction, and then back this way. So they'll be like up and up or down and down. So whenever you have an odd number of turns, you're going to start and end the same way. So I connected it that way. If somebody has a better explanation, please share it, because there are other ways of understanding it.